for the speakers. Vera Maliborode, postdoctoral research at the CNRS in France, with a presentation about digital twin for fast colorimeter simulation. Lorenzo Sprea, postdoctoral research at INFN in Italy, with a glitch flow, a digital twin for the Virgo gravitational wave interferometer. Yuri Pidopirihora, sorry for butchering. I always butcher your name, sorry. Postdoctoral research scientist at MPG in Germany with MLPPA, a digital twin for pulsar studies in radio astronomy. And to close the webinar, we will have Gaurav Sinha Ray, postdoctoral research at SIC in Spain with digital twin for lattice QCD simulation. Each of the 4 presentations will be about 10 minutes long. And at the end of each one of them, we will have about 3 minutes available for any questions. What happened? Okay, so we can give what happened here? Okay. Here we have just started with the introduction of the interTwin project, and then focus on the 4 use cases that I've mentioned before. So a quick overview of the project, which started at the beginning of September 2022, and will, with a duration of 3 years, will end at the end of August this year. It's coordinated by EGI Foundation and has 30 participants representing a provider with resources such as cloud, HTC, and HPC, and HTC. We have technology providers and the community representative from 5 different domains and requirements. Okay, here we give a definition of the digital twin that has been used and agreed. So a digital twin is a virtual representation of a physical object, process, or system. It's created and sustained with information derived from one or many sources of data, such as sensor or models, considering historical as well as real-time data. So, and to expand on this, the digital twin engine is the software infrastructure that manages and supports the creation, deployment, and operation of digital twins. Other than that, okay, to do that, it orchestrated the complex data flow, provide access to the resources needed, and enable services, simulation, data fusion, etc. On the right side of the slide, this is shown graphically with the different layer, but will be described more in detail in the next slide. So the infrastructure, we can see it as composed with the different layers, and at the bottom, the first one, the DTA infrastructure, allow access to the different type of technologies previously mentioned as cloud, HTC, and HPC, and data repositories. These include as well the software needed to federate and orchestrate those computer resources, providers, and data. On top of that, the digital twin engine core modules offers common capability for the digital twins that have been implemented for the digital twin. Those include, for example, modules to configure the resources available to the project, quality assessment, data acquisition and processing, etc. On top of that, we have a layer of thematic modules that are specific for the needs of the digital twin applications. Finally, on the top, we can see the digital twin application, which are also used by the data scientists, the policymakers. The digital twin are in turn developed by the developers that use the digital twin engine to build the digital twin application. The platform developed in the project is based on open source standard and open source technologies. In this slide, there are the use cases that have been identified and developed in the interTwin project. In particular, in this today we will focus on the physics ones that are the four highlighted in red. So digital twin for fast particle detection simulation. Glitch flow digital twin for the Virgo gravitational wave interferometer, MLPA, a digital twin for pulsar studies in the astronomy, and a digital twin for lattice QCD simulation. In particular, we have seen the different layer previously with the thematic module. For this, we have have been developed several thematic modules that are OpenQXD and NormFlow for lattice QCD simulation, Pulsar DT and Pulsar DT++, and Pulsar RFI Gen and Pulsar RFI, and then for radioastronomy, Glitch Flow for radioastronomy, and then 3D for high energy physics. And then, very short introduction, and I pass the microphone and the slides to Vera. I'll stop now.
Yes, hi. Let me know, please, if you can see the slides.
I can see them.
Okay, great. So yes, my name is Vera, and I will present the digital twin for fast particle detector simulation. And at first, I would like to give some context. Why do we need such a digital twin? So we have real particles and particles that are predicted by a model, and we would like to understand how well our model corresponds to the nature. The problem is that we cannot really compare these two directly, because the real particles, they are going through a detector, and detector registers some electrical signals left by the particles. Then we use the reconstruction algorithm to transform these electrical signals to the objects corresponding to their real particles. So from electrical signals to the objects that we are thinking that this is, for example, this kind of particle with such properties, etc. We still cannot really compare such kind of objects with what is the model predicting. So we need to simulate the passage of these predicted particles through the detector. We have then the simulated electrical signals. We apply the same reconstruction algorithm, and now we have the reconstructed simulated particles that we can finally fairly compare with reconstructed real particles and make some conclusions about our model. So that's the framework that we are working in. And the part related with the digital twin is the simulation of the particle passing through the detector. So usually particle detector consists of several layers of different subdetectors. And what is interesting for us is the colorimeter part of the detector. So colorimeter part of the detector, it measures the energy of the incoming particle. So initial particle, it induces, it interacts with the detector material. There are multiple interaction happens, multiple particles that are being born, and this process is called particle shower. And this is usually the most computationally expensive part of the detector simulation. So usually what is done is we use the Monte Carlo simulation with the software called GEANT4 that models literally every interaction that happens inside the colorimeter one by one. And that's why that's what it makes it very computationally expensive. So the colorimeter, it is divided to cells, the whole volume of the colorimeter. And the detection is happening as following. So each cell absorbs and measures the amount of energy from a part of a particle shower that was induced by the incoming particle. So what we need is to simulate energy value in each colorimeter cell, depending on the primary incoming particle type and its energy. And for this use case, we have a digital twin implementing a generative model capable to accurately and fast simulate colorimeter response in comparison with GEANT4 speed. And we have two models, 3D GAN and CALO-INN. I will start with the 3D GAN. So 3D GAN is the generative adversarial network consisting of two parts, generator and discriminator. And the colorimeter signals in 3D GAN are represented as monochromatic pixelated 3D images, with the cell energy depositions being the pixel intensities. So basically, we are doing the, let's say, image generation in this case. This digital twin looks at the colorimeter from the click particle detector. And this algorithm is pretty fast. It's 3 orders of magnitude faster than the classical GEANT4 simulation. And it provides pretty nice results. The problem is that it's still not accurate enough to be used, and it's need or the fine-tuning, or there should be another model. So it's very good to do the preliminary simulations, or it's very good for the very specific cases, but for general cases, it's not accurate enough. So this second model is called CALO-INN. It's a normalizing flow model that learns to transform a simple distribution to a distribution corresponding to the colorimeter response. And the CALO-INN model was chosen based on the results of the CALO Challenge. CALO Challenge, it's Kaggle-like competition providing the benchmarking setup for comparing the generative models for colorimeter simulation. And according to this challenge, CALO-INN model, it keeps kind of a good trade-off between accuracy and generation speed, because usually models are super fast but not very accurate, or very accurate but their speed is not satisfying. This digital twin is based on the colorimeter from Atlas particle detector. And as an output, it provides the incident energy, the energy of a particle that enters the colorimeter, and array containing an energy deposition in voxels of a corresponding shower. So how is it all implemented in interTwin? So the developer can train the model, whereas the settings are done with the configuration file, and the data are, the training data is originated from GEANT4 very accurate simulations. Then within the project, there can be done a processing and training the model, register the model, and then the user, again, with the help of the configuration file, can use some models from registry or retrain the model if needed, and generate as many particle showers, colorimeter showers as needed. So for the 3D gun, the full integration with the project is done, and code and documentation can be found with the links that are provided in the slides. For CalONN model, the release is being finalized, but it's the full documentation will be also available very soon. So about the components that are the interTwin components that are being used. So of course, the iTwin AI, the AI workflow framework for model training and testing is used for both 3D GAN and CalONN. And with the configuration file, there can be adjusted the pipeline, so the steps to be executed, like a preprocessing, training, inference, visualization, etc. The choice of data set and the selection of the particular showers, the generative model architecture and some training parameters, and many more. Then for 3D GAN, there was also use instruments such as Oscar, Interlink, and SQAAS for workflow execution, federated computing, and quality assessment. And for CalONN, there will be MLflow experiment registry used as well. So this digital twin provides two different models for fast colorimeter detector simulations. These models are different in performance and speed, so the user can choose if they need a faster model or more accurate model, for example. Then the models are trainable for different detector geometries. So as I mentioned, for now, there are Atlas and click detector colorimeters that are represented with and available as trained models. But if a user wants to use different data sets created for the different detector geometries, it's totally possible. And there is an ongoing study on the model performance improvement with the focus on keeping fast generation speed. And that's all from my side.
Okay, thank you, Vera. If you want to stop the sharing, maybe Lorenzo can start his presentation.
Yeah, sure.
Thank you.
Hi, can you all see my screen?
Yes.
Okay. Hello everyone. I am Lorenzo Sprea. I'm a postdoc at the INFM in Turin. Today I'm going to present you GlitchFlow, which is a digital twin for the gravitational wave interferometer. This is a collaborative effort. I've worked with Francesco Sarandrea, Alessio Romano, Federica Lecker, and Sara Vallero. I'll be presenting the work, and I would also like to start by giving you a little bit of context as for what gravitational waves are, what is an interferometer, and why we thought of building a digital twin. To answer the first question, so what are gravitational waves? Imagine space as a huge stretchy rubber sheet. And whenever massive objects like stars or black holes move, they create tiny, very tiny ripples in this sheet, much like when you drop a stone in a pond, you see some propagating circles. These ripples in the stretchy rubbery sheet of space-time is what we call gravitational waves. And despite being so tiny, extremely tiny, gravitational waves are as important as they are tiny, because they are a very peculiar type of signal that is not stopped by anything. They pass through everything, and thus they provide us a clear signal from even the most hidden parts and the furthest parts of the cosmos. And so by studying these signals, the scientists can understand extreme physics, they can formulate new physics and uncover the history of the universe, which is ultimately the fundamental question of physics. You may wonder, how do we detect these super tiny ripples? To do that, we need very complex instruments called gravitational interferometers. Currently, there exist 4 of them. There are 2 in the States, the LIGO detectors. There is 1 in Japan, the Kagra detector, and 1 in Italy, in Tuscany, the Virgo detector. Together, they form the LVK collaboration. And to understand how these machines work, imagine them as basically some really big rulers whose length is modified by the passage of the gravitational waves, and thus they measure the distortion of space. In practice, the idea of the rulers is implementing using light and mirrors instead. You can see basically a representation on the slide at the center. So the way it works, you have a monochromatic laser, so with a particular wavelength. They split into 2 beams that travel down to perpendicular arms, and they are reflected by mirrors, and eventually they recombine. And when they recombine, there is basically a detector. So if one of the if a gravitational wave passes by, then one or either of the arms might get squeezed or stretched. And because the laser is monochromatic, so it means that it has a fixed wavelength, we will have basically either some constructive or destructive interference at the detector. And so by measuring how these interference fringes vary with time, we can track basically the passage and detect the gravitational waves. Because these instruments need to measure such minuscule changes, they're also incredibly sensitive to all sorts of tiny fluctuations and noise from various sources, from like something very common like earthquakes, but something also you might not expect, like planes in the sky or strong sea activity some 30 kilometers away. So in order to be precise and not to have basically a lot of false alarms, we need a lot of auxiliary channels keeping track of all of these sources of noise. And by a lot, I mean a lot. It's in Virgo, it's 130,000 auxiliary channels monitoring basically everything they can about the experiment. So you can see an example on the slide of the impact of this noise on the data. Here you can see this is in purple, you have a gravitational wave signal, and in black you have the noise. And one particular type of noise called non-Gaussian transient noise, or glitches for short, is a very significant challenge in the study of the interferometric data, as these glitches occur sadly pretty frequently, and they can look very similar to the actual astrophysical signals on our data, making it hard to distinguish between the data and the signal. They cause false alarms and even hide interesting physical information at times. So our idea to tackle this challenge was to model the interferometer as a digital twin and generate these glitches using deep generative algorithms. The strategy involves mapping glitches from carefully selected auxiliary channels, which of course must be sensitive only to the noise and not to the gravitational wave signals. And we map them to our main channel data. This allows us to generate a model of the noise and then subtract it from the physical interesting data, because our ultimate goal is to perform BITO, that is flagging excess energy in the data as glitches, and this is useful for saving computing resources for further downstream analysis pipelines. And then the noise, that means removing the glitches from the data and give some better, higher quality data to downstream pipelines, basically. The advantage of using deep learning for this task is that, unlike traditional methods, it naturally handles the complex nonlinear relationship present in the data. And to help our model learn more effectively and quickly, we use spectrograms, which are these colored images you see on the slide, which are basically visual representations of showing how the frequency on the vertical axis of the signal change over time, which is the horizontal axis. The color of the pixels from blue to yellow indicates how much energy from less to more is associated with a particular frequency mode at a particular time. The specifics of the data preprocessing and the neural network are reported on the slide. It's nothing too fancy, so I won't go into it. But if you have questions, I'm happy to answer later. And let me just spend a few words on the neural network. It's also nothing crazy. It's a UNet, which is a convolutional neural network, which uses skip connections and attention gates. Attention gates are basically the fundamental building blocks of your ChatGPT, DeepSeek, whatever you like, for generative model that you use every day in your everyday tasks. And these attention gates and residual blocks and skip connections are basically a way to better capture the complexity of the data. All the code is open source and is available at the link at the bottom of the slide. So the neural network is the most important, but not the sole component of our pipeline. You can see the entire pipeline depicted in this slide. So it's composed by two main subsystems: the training subsystem, which is triggered and operated by basically my colleagues and I, and then the inference subsystem, which is triggered by the user, potentially any of you, or actually it's targeted for gravitational wave data analysts, but it's pretty flexible for other use cases. Both subsystems are collections of modules implemented as iTwin AI plugins. I will tell you more about iTwin AI in the next slide. For now, just know that iTwin AI is a Python library developed by the project for basically machine learning tasks. And sorry, I see chat. Okay, sorry. So the pipeline, let me tell you briefly how the pipeline works. The training pipeline starts with the operator applying the pre-processing on the data from the data lake, which I will talk about in the next slide. But before this pre-processing, there's actually one preliminary step that needs to be applied only once, and that is the selection of the relevant channels I was telling you about earlier to train the network with. This is achieved using this Analysa module, which basically is computes correlations between main and auxiliary channels. Then the preprocessed data is fed to the neural network, the glitch flow module, which is trained. And once the training is done, the model is logged into a model catalog, courtesy of iTwin AI on MLflow. And then the model registry, additional informations are also metadata basically is logged onto that as well. And basically the way the user pipeline works is basically, again, pre-processing, then the model is loaded from the model catalog, and then the vetoing and the noising is performed. Sorry, next slide. Okay. Now, as promised, let me tell you a little bit more about the iTwin AI and the data lake, the Rusio. So both of these are part of DT, Digital Twin Engine core and infrastructure integration. So with other working packages of the process, the data lake basically, this Rusio plugin was used to transfer data from our own basically data cluster into a data lake, and basically the advantage of the data lake with respect to databases is that the data is stored in an unstructured way, which is particularly convenient for machine learning applications, as you in principle don't know the relationships of hand. And you can see some information about the size of the data that we used. And iTwin AI, I was telling you, is a Python package for machine learning. And basically, what it allows us to do was to basically, how do we say? Was to allow us to perform some distribution training. I couldn't find the word. Then, of course, logging the model catalog on MLflow, as I was telling you, and then it's particularly the way it is implemented is particularly friendly for user configuration of the pipeline. As you can see in the slide, it's only one line, and then is good for code reusability. Now that you have a better idea of how the pipeline works, let me see how the user can basically set it up. It's fairly simple. As I told you before, it's just one line, this iTwin exact pipeline, and then you specify some further parameters. What do they do? So you can set a few things using this config.yaml file, like the steps and the orders of the pipeline, then the training parameters, like which loss you want to use, learning rate, number of epochs, etc. You can select the neural network architecture, the weights from the model registry, and the path for saving and loading weights, data results, etc., etc. Per-process parameters and steps and data sets. You can see an example of the pipeline running below. And on the bottom left, you see the visualization module, which is integrated in TensorBoard, for which you have on the left your run. This is the training run with the timestamp. And then you can see as the accuracy evolves with the epochs, then you have here some plots that we explain later what they are. And this is basically the between module. So you have a specific code associated to each data segment, and then basically you have your flag that I was telling you about. So it's pretty straightforward to use. Now, coming to the results, you have them on the top right of the slide. So basically, here I have a few plots. I will go through them and I will explain. Starting from the top, you see two accuracy versus SNR. So basically, you have two curves, a blue and an orange curve. Basically the blue curve is telling you how well the model is performing denoising. By denoising, we mean basically that the model is able to correctly remove all of the excess of energy from the real data. This is the real data, this is the generated, this is the difference. As you can see, basically the model is doing a good job. And basically the blue curve is telling you how good the job is. So it's telling you how well we are able to remove all of the yellow from the plots with increasing values of basically of the shade of yellow. For typical values that are relevant for the pipeline, like 4 and 6, we see that the model has an accuracy well above 90%, which is great. And then the orange curve is the vetoing accuracy. So the goal of the DT was successfully implemented, as both vetoing and denoising for scattered light glitches, which is this type of glitches that you should see in the slides, was reached with an accuracy well above 90%, which is great. And this DT is having a good impact on the collaboration as well, on the community, because first of all, we're discussing the integration of the DT into the Virgo interferometer pipeline, whether it's going to be low latency or live or as a side tool for data analysis, we don't know yet, but we are discussing this. And then most importantly, data preprocessing tools are being used by the rest of our colleagues in the collaboration for basically analyzing the data, computing correlations, computing these spectrograms, whitening the data, etc., etc. And just to give you an outlook, we are also discussing ideas to adapt the DT to improve, basically, and clean time domain data, which is a more complicated task. So not clean these images, but these wiggly lines here. And this would be more useful because it would integrate better with the downstream pipelines, which work on time domain data. And this will improve greatly the quality of the data and reduce false alarms. And with this, I am done, and I thank you for your attention.
Thank you, Lorenzo. I also don't see any question in the box again, but okay, just a reminder of the Q&A box. If you have anything, maybe we can also pick it up at the end in case. So, okay, thank you again. I guess we can then move to Yuri. You want to share or?
Yes.
Okay.
So can you see my screen?
Yes.
Okay. So hello, my name is Yuri Pidoprihara. I'm from Bonn, Germany. I represent Max Planck Institute for Radio Astronomy. And we lead this project, but it's a collaborative effort of several scientists from a few German institutions. And this is the radio astronomy use case of interTwin. Okay. So we live in very interesting time from the radio astronomy point of view, because right now very massive new instruments are coming online. The most important one of them is, of course, a square kilometer array shown here in the image, built in 2 countries in South Africa and Australia. It will be fully operational in a few years, but it's pathfinders, so like smaller versions are already in operation. And of course, it's very exciting from the scientific point of view, but one problem with it is that it's gonna produce really big amounts of data. And it's first time in the radio astronomical history that the data is, the amount of data is so large that it will not be it will not be possible to process it in the usual way of keeping it for a long time, archiving, and then dealing with it with human experts. So some other ways are needed. So we can keep it's either for a very short time, or if you want to keep for a long time, we need to choose only a tiny part, something very significant. So we need some sort of method of making decisions on that based on incomplete information. And this would lead to data irreversibility. And to deal with this, basically, we need to create a feedback loop between the sensors, in this case, telescopes, and the processing centers that can assess the data very quickly, preferably in real time or near real time, and then keep only what's scientifically important and delete everything else, and then also guide the telescopes based on these decisions and adjust the observations themselves. So as a pilot project in this, trying to create such a system, we built the MLPPA, which stands for Machine Learning Based Pipeline for pulsar analysis. Why pulsars? So there are 2 reasons. First of all, pulsars are very convenient from the point of view of this sort of decision making, because the pulsar, it's a fixed astronomical object. We know where it's located. We know how it emits the signals. So it emits a short pulse, and it's quiet, and it emits another short pulse. And if you observe it continuously, you collect a lot of data that contains some pulses, like maybe 0.1% of the data will contain pulses. Everything else will contain noise and all kinds of radio frequency interference. So this is a nice object to start building this sort of system. And the data that we are working with, they look something like these 2 boxes shown in the lower right corner. One shows the actual pulse of a pulsar, In the x-axis here is time, the y-axis is frequency. And the other box shows the radio frequency interference. In this case, it's broadband, so it's for a short time, but all over the band. There could be also narrow band interference. It will be a stripe, but perpendicular to this one. So we need to distinguish between these sorts of images and also completely empty boxes with just noise, and sort them out and keep only the pulses. So this is the basic task that we are performing. The data we're working with comes from a few pulsars, including the brightest and the most famous one, the Crab pulsar shown here. And it was observed by two telescopes, the Effelsberg telescope that is located here in Germany near Bonn, and Meerkat, which is a new array, one of the SKA pathfinders that just started observing and producing new data. And this shows the basic diagram of our system. So the general idea is that we deal with the data stream, we sort it out, and based on training, and training is performed using digital twins. And here I want to show the more detailed diagram of how it's organized. So the original data come from either directly from the telescope if it's real time, or more likely from some external data repository where it's temporarily kept. And that's why it's nice to have a buffer like a data lake here. So the data and the data here is shown with green arrows. It can go to the data lake temporarily, and then it can be sent to our system. So if the system is already trained, then it just goes to the ML classifier, and the classifier basically sorts it out. It looks into different frames and keeps labels each frame in accordance with what it is with pulse or RFI or empty frame or something. But of course, it needs to be trained, and it can be trained also with the real data. But the problem here is that, as I mentioned, pulses would be only like 0.1% of the whole amount of data. And this is a problem because that means that the training will be severely biased against exactly the type of frames that we want to detect. So it is much better to create a digital twin, which would create the necessary types of frames with necessary signal to noise ratio. And that's exactly why we build this digital twin here shown in the upper part of this diagram. And the red arrows here show the simulated data that can come to the training block, and they train the machine learning classifier, and then it can perform. And then the labels produced by this system, they send to an external decision-making system, which is not part of this project. So the main components of this, one is the digital twin of pulsar observation, and it's based on a very sophisticated multi-spark model of pulsar as an object, the neutron star that rotates and emits this complicated beam of radio waves. With here you see an example of pulses that they have very complicated structure, plus the propagation through the interstellar medium ISM, plus you can choose various types of radio frequency interference, plus noise. And there are different kinds of lines that you can choose and parameterize it. And at the end, it's all mixed and comes down to whatever you want. The second important component of this pipeline is the convolutional neural network expert system that basically makes decisions after it's trained. The key feature of it that I want to mention is that it includes the so-called transient X module that translates this classical spectrogram time versus frequency into time versus dispersion measure, DM, axis. And this allows, as it's shown here in these two images, that in the classical spectrogram, you cannot really see the pulse. It looks like a pure noise. And in fact, it contains a pulse with the signal to noise ratio of about 10. But when you transform it using this transient X to the DM time plane, then you can see this bright pulse here, and this allows to detect it with much more certainty, the weaker data frames. Another thing I want to mention here is the link. It's the full set of data and trained models and that would allow for anybody to play with this and understand how this works. Finally, an important part of this project is efficient software implementation. And one of the problems, of course, that dealing with such large amounts of data, we need to apply high performance computing. And this means special type of efficient programming. So most modern radio astronomy software cannot be used with HPC centers. We've tried, we've did tests. Usually you can use only a few cores, and then it either crashes or there is no real benefit. So this is that's where the Pulsar DT++ module comes from. It's the previous modules which were written in Python, rewritten in C++, specifically to be convenient to deploy and convenient to use with HPC centers. And everything is well organized and put into GitLab repository shown here. So the impact and future use of this project. So one of the institutions that just emerged during the existence of this project was the German Center for Astrophysics, abbreviated in German DCA, which will be one of the main centers, at least in Germany, to deal with this data tsunami coming from the new telescopes and from SKA in particular. And it actively participates in this, and basically MLPPA becomes a pilot of how to deal with the SKA data. But in general, it's also the intent, as is shown here, that to build a big cloud of all kinds of different databases and data repositories that can be organized and sent to various type of hardware available at the DCA, and the range of this hardware is impressive, and to be organized or based on the ideology shown here in interTwin. So this will be the legacy of this project. So it's all for me. Thank you.
Okay, thank you, Yuri. Again, I see no question at the moment, and we're a bit late, maybe. So I guess we can move forward with Gaurav. Okay, you can share. Perfect. So I leave the microphone to you.
Hello, everyone. Yes, I'm Gaurav Ray. I'm a researcher from CSIC, and I've been working on the digital twin for lattice QCD simulations, which is a collaborative effort by researchers here at CSIC, which is the Spanish Research Council, and researchers at ETH Zurich over in Switzerland. So as a bit of an introduction, first, let me talk about the standard model of particle physics, which is basically a physical theory that incorporates almost everything we know about subatomic physics. So what subatomic particles exist, their properties, and how they, in particular, how they interact with each other via the 3 of the 4 known fundamental forces. Those 3 forces that are described in the standard model are the electromagnetic force and the weak and strong nuclear interactions. So with the notable exception of gravity, the standard model describes all the interactions in the universe. And the standard model itself is described by a series of equations, field equations, quantum field equations, and a bunch of parameters that are used as input into the standard model. And once we put those parameters in, you can calculate the properties of different particles. So basically, by solving these field equations, we can find out how particles interact and how they evolve over time. So that the digital twin that we're talking about here is basically it's how particles interact at a subatomic scale. And that's what we're looking to reproduce digitally. So quantum chromodynamics is it's the part of the standard model that describes strong interactions. And it describes strong interactions between particles called quarks and gluons. Gluons carry the force, and the quarks are the particles which interact with each other. So for example, the proton and the neutron are each made up of 3 quarks. Now, quantum chromodynamics is notoriously difficult to solve using traditional methods because it's highly nonlinear. So the method of lattice QCD provides a numerical method to solve those field equations, and it's basically based on the path integral formulation of QFT, and it involves taking an infinite dimensional problem and reducing it to an extremely high dimensional but finite problem. So the way it works is you basically take a continuous region of space-time and then you split up this continuous region into discrete chunks, and then you can simulate those discrete chunks on a computer using what are called Markov chain Monte Carlo simulations. Now, these simulations are basically boxes on the order of femtometers. So that's 10 to the minus 15 meters. So we're looking at basically how quarks interact with each other. These simulations are done with different resolutions. And the idea is as you go to higher and higher resolution, you're coming closer and closer to continuum spacetime, which is what we want eventually to be able to simulate. So despite the success of lattice QCD, basically generating these so-called lattices, which we use to do these simulations, using these simulations, it's a slow process. It requires a huge amount of computational power. And as you get to higher and higher resolution, a bunch of sort of algorithmic issues get worse and worse. In particular, this notion of high autocorrelation times. So many people in the lattice community have been looking for alternative methods to Markov chain Monte Carlo in order to do these lattice simulations. And I mentioned that there are lots of successes with lattice QCD, and I just want to mention 2 successes briefly. So one success is if you combine quarks, like I said before, you can get protons and neutrons, but you can get a whole bunch of other particles as well. Basically, if you combine 2 or more quarks, you can get dozens of composite particles, And we've measured experimentally the properties of these particles in particle physics colliders in real experiments across the world, especially the Large Hadron Collider, which has measured dozens of these. I think since the LHC turned on over a decade ago, they've discovered something like 80 new composite particles. So you can compute the masses of these particles using the lattice QCD method, and you can compare them to the experimental numbers, and it turns out the lattice QCD simulations have done very, very well. The other success, which is more recent, is the anomalous magnetic moment of the muon. So the muon is like the electron in every respect, except it's much heavier than the electron. It has this property called its anomalous magnetic moment, and you can calculate this on the lattice, and you can measure it at an experiment. The experiment is actually in Fermilab in the USA. They've measured the anomalous magnetic moment very, very precisely, and it's been calculated on the lattice very, very precisely, and the results agree very well, which is a theoretical confirmation of the standard model. So in terms of lattice simulations, not only do they require a lot of computational resources, they also require increasingly now a lot of storage space. Basically, these lattices that you generate can be reused for future calculations, and these lattices are getting bigger and bigger. So one of the things that the digital twin engine from interTwin provides is this idea of a data lake. The reason that a data lake with a federated identity is so useful for the lattice community is that, like other scientific collaborations, lattice collaborations benefit from economies of scale. Lattice collaborations are highly international, and researchers move between institutions a lot of the time. So it's useful if you have a fixed federated identity that you can use to access all the lattice data that you've generated, say, in your career, or all the lattice data that your collaboration has generated or has access to. So to address this challenge of data access, the WP5, so the data lake developers, have helped us create a lattice data lake, which has 3 endpoints, 2 in Germany and 1 in Spain. Importantly, it can be authenticated using the International Lattice Data Grid, which would be the provider of this federated identity, which is very useful because the International Lattice Data Grid hosts 2 important catalogs, the metadata catalog and the file catalog, these are meant to be sort of central repositories where all sorts of lattice collaborations can register and upload their data with these catalogs. And so the idea is that if we have a lattice data lake, which includes access to these 2 catalogs, then that'd be extremely useful for lattice researchers. And this data lake is in the process of, it's constantly being developed. And one thing that is being developed at the moment is an endpoint in Spain with access to the standard HPC file system, which would be useful because then you could generate data using a lattice simulation. It could be a traditional lattice simulation, or it could be a machine learning simulation, as I'm about to describe, and then it would go straight into the data lake. So challenges for lattice simulation. So for a typical lattice simulation, you need to generate several what are called ensembles of field configurations. So these are just collections of lattices with different resolutions and multiple values of parameters of whatever theory you're interested in. It's highly expensive to generate, save, and transfer these field configurations, and it gets worse as you go to higher resolution. So the focus of this use case is to explore whether machine learning-based generative models can generate field configurations for lattice QCD with different parameters and resolutions in a more efficient way. Therefore, we can basically, instead of having, as a benefit of that, instead of having to save and transfer these field configurations, you would basically train a model against a theory, and then you can save and transfer the trained models rather than the field configurations. And as an example, I have this plot here from a typical lattice collaboration where each circle represents a different ensemble of lattices. and they've basically, you've got increasing resolution towards the left, and then the pion mass, which is an important parameter for lattice simulations, on the y-axis. So to explore this machine learning generative approach, we've developed the NormFlow thematic module. So the NormFlow package, it basically provides utilities for implementing the method of normalizing flows as a generative model for lattice field theory. It currently supports simulating scalar theories and has limited support for gauge theories. And gauge theories are important because gauge theories form the heart of the QCD, or part of the standard model. The NormFlow, it's a PyTorch-based package. So because it's PyTorch-based, it already includes many methods and functions to make doing machine learning simulations easy. And it also includes lots of modified classes, which have been modified specifically for lattice simulations, lots of linear algebra modifications, and modifications to the backpropagation algorithms that are specific to NormFlow. Part of the digital twin engine involves implementing these good software research practices through the software quality assurance as a service, and that has been integrated with the NormFlow package. In addition, we have a integration with the iTwin AI library, which provides methods that can be used to kind of tweak the distributed training, and perform logging and profiling. And I put an example here in the plot on the right, which is basically looking at the scaling of the energy consumption with the number of GPUs when you choose different distributed training frameworks. So the standard distributed training framework that we would use is Torch DDP, Torch Distributed Data Parallel, which is what comes with PyTorch. But then you can also use Horovod and DeepSpeed, which are alternative distributed training frameworks. And you can not only look at their energy consumption, but iTwin AI lets you look at the performance, the communication bandwidth, and other things like that, which is useful for profiling the code. So the specific machine learning generative approach we're using is called the method of normalizing flows. I think it's important to note that here we're not training a model against external data. We're training a model against basically a theory. The theory defines a probability distribution. So the probability distribution can be quite complicated. And so it's basically self-training against a neural network against that probability distribution. And this diagram on the bottom kind of describes what happens. You start with a prior, you have a transformation, and then you compare that against the action using a loss function. And then if you want, we can design hybrid methods, which kind of incorporate the machine learning part, and then also the traditional metropolis accept reject step, which is what you would get from traditional Markov chain Monte Carlo lattice simulations. So each model within NormFlow has basically three key components. It's got a prior distribution from which to draw initial samples, a neural network to perform a series of invertible transformations on the samples, and an action that specifies the target distribution. And I've had this snippet of code here, define make model, which kind of shows you how easy it is to define a model from which you can then train. The purpose primarily of NormFlow is as a sort of a digital machine learning sandbox in which you can try out different neural network architectures. So there are lots of several predefined neural networks that come with the package that have been designed because we know they work well when training against specific theories, whether they be scalar or gauge theories. Those are things like coupling layers with affine transformations, rational quadratic spline transformations, or this power spectral density flow. And as an example on the right, I have here an example of a training plot, which plots the ESS, which is the effective sample size. It's a metric of how well the model has learnt our theory against training epoch. And here we're basically comparing different types of priors and different types of networks against each other to see how well which network and prior combination gives you the best performance. So norm flow, primarily, it's for researchers who want to explore the application of machine learning methods to lattice simulations by, as I said, by designing these new network architectures. And then by being able to quickly implement the new network architectures and get results fast. It's also for developers who want to improve the performance of the norm flow package by implementing algorithmic improvements, for example. And so here we kind of see a flow chart of kind of the typical workflow for a DT user on the top. They need their network, their physical theory, and their prior. They train the model. Once you have a trained model, you sample lattices from the model, and then you go to interesting physics with those lattices by calculating observables, for example, like the pion mass I mentioned earlier. So just as some concluding remarks, so NormFlow, it's a Python package that can simulate scalar theories and gauge theories using neural networks and normalizing flows. Researchers in the lattice community can experiment with novel neural networks. The code is publicly available on the interTwin GitHub repository. More developers are needed for efficient lattice QCD simulation, especially at higher resolutions and larger lattices. And so far, this work is proof of concept. We hope to enable precision research by integrating NormFlow with some of the more traditional lattice codes like OpenQStarD. And this prototype lattice data lake that I briefly mentioned points a promising direction for data management within the lattice community. And I'll end there. Thanks.
Thank you. Okay, I don't see any question again, but if you have one, you can quickly write it as we run a bit over. And I want just to remind you, next week on Tuesday, the 1st of July at 2 p.m., if I'm right. There will be the second, 2 p.m. There will be the second part of this webinar dedicated to the environment science. So if you wanted to join that part as well, please feel free. Still don't see any other questions, so I guess we can close here. Okay, I've seen that Gwen pasted the link on the chat, so that makes it easier to register. Okay, then I guess we can close here.